these notes are an introduction to acid and base. We're going to get into some naming. We're going to look at definitions of acid and base. We're going to look at the pH scales and pOH scales, and then how to calculate in between those. So starting out with naming, we are going to look at acids. And why we look at acids is they are a little bit different than our normal naming methods that we've used in the past. So we have what I like to call simple acids, where you just have a hydrogen that's connected to something else, and it's one piece. So here I have the example H2S. You could have HCl, you could have HF, but they're all going to be kind of named this same way. And so what we're looking at is this is named hydrosulfuric acid. And this S here is giving us this sulfur in our name, in our hydrosulfuric acid. And then the prefix hydro and the ic acid are just naming tools that we use. So this is a hydrosulfuric acid, and these are our simple acids where we have one nonmetal and then our hydrogen that are connected to it. Our next example starts to get some oxygens involved. And oxygens, depending on the number of oxygens we can have an ITE or an ite ending, or an ATE or ate ending. And that's what we kind of need to look at to determine our name. So if we look at SO3, we name this sulfite. So the acid name has an OUS ending. So we still use the same sulfur. And then we add OUS. So sulfurous acid. So again, we're getting this is giving us our SO3 is giving us our sulfur, and then the ITE ending gives us this OS acid. If we look at H2SO4, SO4 is sulfate. This is named sulfuric acid. So again, we have from the sulfur base, we have sulfur here, and then from the ATE ending, that gives us an ic acid. And these are the three ways that we would name, the three categories for naming acids. So you have just your standard acid where it's one nonmetal with our hydrogen, and we call that hydro, and then the element ic acid. So H2S, hydrosulfuric acid, HCl, hydrochloric acid, HF, hydrofluoric acid. Then we start adding oxygens in, and if we have an ITE ending, like we do in H2SO3, we're going to give it an OUS and then acid. If we have an ATE ending, like we get from SO4, then we're going to give it an ic acid. So a couple other examples of these would be chlorate would be chloric acid, whereas chlorite would be chlorous acid. Then we also have our bases. And our bases, they just get your standard naming. So a base of NaOH, we would name it like we have learned in the past, sodium hydroxide. Okay, so let's look a little bit closer to our acids and kind of get some definitions in here. We like to talk about really two main definitions for acids. We have what's called Arrhenius. And Arrhenius really centers around when you put an acid into water, it creates H plus if I can spell water, in water. All right, so what we're looking at is we have Cl minus with an H plus attached. Then we also have water, okay, with our oxygen up here and our hydrogens down here. Now, water is a molecular compound, meaning that it shares its electrons between all pieces, but the oxygen tends to like the electron more, so the electron spends more time up there, and we say that this is slightly negative and this side's slightly positive. So there are some bit of charge on a water, but it's not that the oxygen is fully negative and the hydrogens are positive, because there's some sharing, there's some going back and forth. Well, this water molecule is going to wedge its way in between here, making its oxygens point towards the hydrogen and the H plus, and then the hydrogens of water point towards the chlorine. And it kind of really just squeezes in between here. And what we notice is we'll get Cl minus and H plus will separate, and we'll have all of these waters kind of surrounding them. So this is kind of the Arrhenius definition, where we're going to have this separation because water's kind of involved, and we create this H plus. One thing to note about the H plus ion, so it separates when we get put in water. So there's all this water floating around. We usually have a water that's going to orient itself and kind of be attracted, because the oxygen side is negative and the hydrogen is positive, so it's going to be attracted to that hydrogen. So what we were calling H plus ion can be referred to as H3O plus, because we have this water that's hanging around pretty close. These two terms, H plus and H3O plus, they're interchangeable. You can use one or the other. So if you see H plus, it means H3O plus, and if you see H3O plus, it means H plus. So our other definition that we have is a Lewis acid. And this one is a little more broad. Kind of Arrhenius locks us into requiring this H plus, and so Lewis kind of took a step back and said, is there any way we could make this more general so that it fits all acids, and maybe not like 99% of them like the Arrhenius definition does. And he found that acids can be electron acceptors. And that makes sense, because we have this H plus that's floating around, and it has a spot for electrons to go. So there's our little electron that wants to get onto our hydrogen. So these are our two definitions of acid. Arrhenius means that it creates H plus when we put it in water. Lewis says that no, acids are electron acceptors. All right, so now we're looking at bases. And of course we have our same two definitions. We have an Arrhenius definition. And the Arrhenius definition says when in water, it creates OH minus. And in this case, there's two ways to do it. First, the base has OH minus. That breaks off. So let's do, for example, we'll do NaOH. So NaOH is going to break apart Na plus and OH minus. So right there is your OH minus that has broken off. And the same thing where water that water particle kind of wiggles its way in between here until it just kind of breaks them apart. This time the oxygen side will orient itself towards the Na plus and the negative, and then the positive hydrogen side will try to get near the OH minus. So this one's pretty simple, and it's pretty easily identified that NaOH is a base because it has OH. The other type is when a base takes H plus from water and leaves OH minus. Example of that would be NH3 plus H2O. The NH3 is going to take a hydrogen and make NH4 plus, and then we're going to be left with OH minus from the water. So we're really kind of stealing from water to make OH minus. There wasn't an OH minus in NH3, so they kind of stole from water and made OH minus that way. Our Lewis definition is that bases are electron donors. And we can see that in the OH minus. It has an extra electron floating around. That's what gives it the minus. So it can donate that or give that away off of that OH minus. Okay, pH. So this really stands for the potential of hydrogen. Or we're looking at how much hydrogen or this hydrogen concentration we have in a solution. So we look at or remember that can also be H3O plus. All right, so we have the pH scale. And the pH scale is showing us this concentration. It's from 0 to 14, and it's based off of a negative log scale. So for our purposes, we're going to look at this and think that we have opposite. We're going to think opposite. So on the pH scale, a very low number, so something less than 7, is going to be considered acidic. Okay? But that means, since we're dealing with opposite, that means we have a lot of H plus ions floating around. Okay? So a lot of H plus ions mean a small pH number. Then we have above 7 is considered our basic solutions, and 7 is our neutral solutions. An area that we don't really look at or have a lot of common experience in is the pOH scale. And this one is looking at the potential of the hydroxide or that OH minus. And it kind of makes sense. OH minus, pOH scale. And in here we're looking at the concentration of OH minus. Same kind of situation with the POH scale. It's 0 to 14, kind of based off of this negative log as well, so this negative log relationship. That means that low numbers on the POH scale are basic. High numbers, so above 7, are acidic, and 7 is still neutral. So a really low number like a 0 or like a 1 or a 2 means that we have a lot of OH minus floating around in that solution. Whereas a higher number like a 12, 13 means that we don't have a lot of OH minus. So we're looking at that opposite again because of this negative. All right, time to look at some calculations and how we can describe these solutions and the degree of how acidic they are or how basic it is. Since we were just talking about the pH and the POH scales, it's probably a good place to start. So both scales go up to the 14, from 0 to 14, and they're kind of opposite of each other. So something that scores very low on the pH scale is acid, but then it would score really high on the POH scale and be considered an acid. So those two are related in the equation of pH plus POH equals 14. And this is useful in that if we want to solve or if we want to find out the OH minus concentration or the base concentration, and we are given the pH, we can get it into POH and then use some equations I'm going to show you in a minute to figure out the concentration. But this simple addition equation is quite useful. So before I continue on and we start talking about concentration, there is kind of a writing technique that scientists use, and they use brackets. And these brackets mean molarity or concentration. And they use those in place of putting units at the end. So if you put these brackets around, then you are able to not use your units meaning molarity because the brackets mean molarity. So we have H3O plus equals 10 to the negative pH. And that's because we're using this negative logarithmic scale and we're using a log with a base of 10. So this works. To do OH minus concentration, it's the same equation. We're just going to look at POH. So these are how we get concentrations. And like I said, if you were given pH and you wanted to find the OH minus concentration, you can do the first equation to get POH and then put it into this last equation to get the concentration. Now, to find pH from a concentration, we're going to use the negative log of the H3O plus concentration. To do POH, we're going to do the negative log of OH minus concentration. So I hope that you see that there is like this little pattern here that really it's the same two equations. These are the same two and these are the same two. They're just looking at pH and H3O plus or POH and OH minus. Now our concentrations are related to each other. H3O plus and OH minus, when multiplied together, of the same solution, when they're multiplied together, they will equal 1 times 10 to the negative 14th. So a combination of these 6 equations can help you solve any and all of the required calculations to describe any acid or base solution.